Rheostats, potentiometers, and resistance spools. A rheostat is an adjustable resistor, and there's an example of one. We have this wire. It's a wire coil wrapped around many times around a cylinder. Then we have a slider here that has a conductor that makes contact with the metal wire. Then we have three terminals, and you can either plug a banana connector into there, a banana plug connector into the gap there, or you can have an alligator clip or something else by just turning this thing counterclockwise, spinning it open, putting the clip in here, and then tightening it up by spinning it to the right. The length of wire, and that's this coil over here, how much wire you have in there, that will determine the total resistance contributed to a circuit when you connect it either to terminals A and B or between terminals A and C. More wire results in more resistance, and the equation for resistance is rho L over A. Okay, rho is a constant, the resistivity depending on the wire, what it's made of. This is the length of the wire, and this is the cross-sectional area of the wire. We're going to keep A constant and just change the length. Current can flow into terminal A. Let's say we connect up terminal A here to a battery, and then we're going to go out terminal C, and maybe we have a light bulb or something else. So the current will flow through terminal A, flow through all of this wire, which is wrapped around a cylinder, then come out this cylinder and go out terminal C. This image shows that approximately half of the maximum resistance of the wire, the total wire here, is used in the circuit by connecting terminals A and C. No current is flowing through here. It's going through terminal A, through the wire, and up through the slider. Rheostats are generally useful in any circuit where variable resistance is required. This makes them great tools in the lab when experimenting with electricity. And the example shown on the previous slide is clearly a lab piece of gear. You're not going to have that in your home if you need variable resistance. And where do you use it in your home? Well, they'd be volume controls on radios, light dimmers, and controlling the speed of electric motors, but they're a lot smaller and made quite differently. And here's the symbol that you use when you draw a circuit diagram. Here's your resistor here. You just put an arrow through it so you can vary it. Sometimes people have a box for a resistor and they put the arrow through it. And this actually symbolically looks like the rheostat. Current coming through here goes through some of the windings, the wire windings, and then comes out here. So that gives you an indication that the resistance has been changed, and it can change by moving this arrow right there. A rheostat can be used to supply a constant voltage available to a circuit load, regardless of that load. In this configuration, it's called a potentiometer. This time, all three terminals are used. We'll establish one part of the rheostat as a resistance in front of a parallel arrangement of the other side of the rheostat and a circuit load. The first part of the rheostat decreases the amount of voltage available to the parallel configuration of the load and the other resistor. We will move the rheostat slider to change the amount of voltage available to the parallel configuration. That's a lot of words. Don't worry if it doesn't make sense now. We're going to have some slides coming up that will illustrate it. If only two terminals of the rheostat are used, then the voltage delivered to a load changes as the load resistance changes. The rheostat configuration does not deliver a constant voltage, which is really what you want from a power supply. So let's see why not. Here's the voltage. It's equal to the current coming out of here times the equivalent resistance of your circuit. And remember, V is fixed. This is a fixed voltage. So we find that the current depends on the voltage divided by the two resistances. Then let's figure out what the voltage drop across the load is, which you would like to keep constant no matter what load you put in there. So we substitute in for I, this term here, times the resistance of the load, and then we do a little rearrangement and we get this. So you would like VL to equal some constant times the voltage, some fraction of the voltage delivered. But if you swap out the load for a different load that has a different resistance, see how it's a function of the resistance of the load? So the voltage will change depending on who we put in there. That's not what we want. So how do we get a constant voltage delivered to the load no matter what the load is? We're going to use 3 terminals of the potentiometer. That will create 2 parallel branches of current, B and C. So you have your current from the battery, and your battery is a fixed voltage. Some of it will go here. That'll be the current to the circuit load. The other will flow through here, come back, and then go to the battery, the tail end of the battery. So let's put the battery here, okay? And then this will go to the load, and then eventually also join up at the other end of the battery. We're going to show that schematically a little better later on. All you need to know on this one is we're creating 2 paths for current to flow through the rheostat, and because of that, we're now calling it a potentiometer. A little more detail on what happened on the previous slide. Once again, we have current coming from the battery here at a fixed voltage. It then splits between branches B and C. But what happens with the yellow resistance here? That will reduce the voltage supplied to both branches, and those branches are in parallel. So we have some current going this way and some going this way, which means you have a parallel operation between the AB path and the BC. This guy comes back to the battery. This goes to your circuit load, and let's just put the ubiquitous light bulb there, and then that will go back to the battery also. And this will be a lot clearer when we draw the circuit diagram, but I just wanted to show you the physical path it's taking. And here's our circuit diagram. You have current coming from the battery. That's the physical part, so we show the battery here going through point A. It then hits the rheostat configuration. Some of it goes through the slider and to point C. Well, that's going to be this path. And that's going through your circuit load. The other part that splits is now going straight back to the battery through B. So that's this back to the battery. And then here's the load also going back to the battery. One more step on the circuit diagram, and this is the great thing about circuit diagrams. You can just sketch them, draw them, cut them to pieces, and you don't have to worry about doing anything physical with the equipment. So we're going to simulate the rheostat now by dividing it into 2 equivalent resistors at the slider position. So here's what we had on the previous slide, and what we're going to do is break this up. And you'll have one equivalent resistor, which we'll call the resistance in series. And what is that? That's the yellow shaded area. Then the other piece here is after the slider that goes back to the battery. And then we have our load here. And here's the slider connection. We've reduced the slider connection to just a line. So we now have 3 resistors where this one and this one are virtual resistors that represent the total resistance of the rheostat. We will fix the slider position so that the rheostat in series equals the rheostat in parallel resistances. So we're fixing these 2. This will reduce the overall voltage coming from the battery, and this one, which is in parallel with the load, will maintain a almost constant voltage to the load. So let's go through the equations and see how it does that. We're going to do a little abbreviation here so we don't have to keep writing out the word rheostat and load, because you can see we have a lot of letters here. Our total equivalent resistance now will be the resistance in series of the rheostat, and then these 2 guys are in parallel. So that equation would be 1 over R SP plus 1 over RL to the -1. Remember, we take the inverse. We then do a little bit of algebra here, and I won't go through the letters, but please check it yourself. And we find that the equivalent resistance is now this term. Now that is way too complex to deal with as it is, so let's move to the next slide and see how we simplify that. Before we simplify it, we're going to make it a little more tricky. So here's what we had on the previous slide, the equivalent resistance of the entire circuit. Then the current delivered out of the battery will be the voltage, which is fixed, divided by R equivalent. And that's this term here. Now we want to find the voltage drop across this configuration. Right? These 2 are in parallel, so they have the same voltage across the rheostat in parallel and the load resistance. So to find that voltage, it will be the current coming here out of the battery. Remember, the current is constant through point A, and then it's going to split here. But the voltage across both of them will be that current times the equivalent resistance of these two guys. So we have our voltage, our total voltage, times this. That's our current. This term here is the current, okay, times V. Sorry, I forgot about the V. And then what's the equivalent resistance of the load resistor and the parallel rheostat? It's this. And then we multiply through, some things cancel out, and we have this as the voltage across the load. Now you're going to look at that and say, well, that doesn't seem constant. I don't see how you can make any assumptions about that. Well, that's what we're going to do on the next slide, and this is a fairly common trick in physics. The equation on the previous slide is absolutely correct, and it's right over here. And mathematically, we would stop right here because why? Math is perfect. However, when we go to real-life applications, when we use a potentiometer, the load resistance is typically much, much greater than the rheostat resistance. So that's how we translate math into the real physical world here. So that means if the load resistance is much greater than the rheostat in series resistance and the rheostat in parallel resistance, then we can make this assumption. You multiply the two resistances of the rheostat and we'll say that's about equal to 0. Okay, this means much greater than, and this means approximately. And that's good enough for us here. So, but what is RS and RP? That's just the total resistance of the rheostat. Remember, we split it into two virtual resistors. So we have our equation here, and we just said because the resistance in the rheostat is so tiny, when you multiply the parallel portion times the series, that's basically 0. That enables us to cancel out this term here. We now have this. We factor and we divide, and we find that the load voltage depends on the voltage supplied by the battery times the resistance of the rheostat in parallel over the resistance of the rheostat in series and the proportion that's in parallel. Has nothing to do with the load resistance, so it's essentially constant. So what we've done here is for a fixed rheostat resistance, we've showed that the potentiometer hookup using all three terminals of a rheostat delivers a constant voltage. Now we're going to move on to the resistor spool, which is a lot simpler. The resistor spool has 5 or 6 spools of wire and screws here which act as terminals. To use the first spool, you need to connect the first and second screws to the circuit. So you would have current coming in, going through all these windings here, and then coming out here to the rest of your circuit. If you want to use the second spool, well, you would go to this one, go all the way around, you would come out here to your circuit. Each spool has different resistances based on the gauge of the wire, which is its thickness, so that would be the A term in your resistance formula, the material, that would be your rho, the resistivity, and the length. The resistances are typically labeled on the spool or in the documentation that accompanies the spool. So obviously you can get one resistance by going here out to your circuit, but you know what? Then you could also go from here to here, then connect up to the next one, pick that one up, and then go out this way. So you could add them in different ways depending on how you're hooking up your wires.